All right, folks, here's a recap on today's lesson. It has to do with this equation over here. Y equals to PERT. This is usually in the context of half-life, growth, decay, continuous compounding for interest, population growth. Okay, they use this equation. Okay, another way of writing it is CEKT. I like PERT because P is your initial amount, okay, your principal, okay. R is your rate, whereas K is not really that intuitive. I don't even know what word K stands for. Maybe constant, but that's not descriptive enough. I like just rate because that's truly what it is. Okay, so P, capital C is your initial amount. Okay, this is not quite, the arrows are not quite pointing to the right places. There you go. Okay, so C or P is your initial amount. Okay, K or R is your rate, and T is your time, obviously. Now, a lot of times in calculus, not a lot of times, sometimes they're going to give you this, but if you take the antiderivative of this, you're going to end up getting this or that. Okay, I like using this version. Okay, now, so when you see this, just jump straight to here. Okay, and at the end of the video, I'll explain how they got from here to there. Okay, I'll explain that this whole thing right here, but that's not necessary. Just know this, you take the antiderivative of, and you get this, and you end up using this. Okay, they just add this little annoying hurdle in the beginning and disguise this as this right here. Okay, so we're going to be using PERT. So now, here's a problem with you don't need this. Okay, I got a way that's shorter because if I show you this and tell you to memorize this, that's one more thing to memorize, and you don't need that actually. Okay, you'll see in the next example. Okay, so let's look at this example over here. Again, I told you that anytime you see this yellow highlight, you think what? PERT. Okay, so Y equals to PERT. So look at this green over here, and we're just going to start plugging in. Okay, we're going to start plugging in. So watch this right here. Okay, now so this becomes that. Okay, and we're going to plug in 0, 40, 0, 40. Does that make sense? All right. K, remember, it's the same thing as R. Okay, we're going to plug in green, green. Does that make sense? Okay, and so this is what I have after plugging in is this 40, 0, we don't know R, P, excuse me, we do know R, sorry, I misspoke, 3.2 times, okay, now this is super convenient. What's anything times 0? 0, okay, and then anything to the power of 0 is what? 1, so ultimately we're going to get this times 1, and P equals to 40. Does that make sense? Okay, so our equation here, we're just going to plug P back in. Okay, P is going to be 40, 3.2 for R, and that's it. We just built our PERT equation. Now, let's say, what's the use of this? Let's say that you want to find the final amount, which is this, after 2 years. Well, what do you plug in for T? 2. Okay, that's why this is useful. If you want to find the final amount after 5 years, well, you plug in 5 for T. We good? Okay, let's keep going with this. Okay, we got 2 more examples. Okay, now I go about this my own way over here. Okay, let's go ahead and cover this up so it's not too, the slide is not too busy. Okay, boom, boom, boom. Okay, now I told you anywhere you see yellow, this thing right here, you think that. Okay, when you take the antiderivative of this, you end up getting that. Now we're just going to plug in a whole bunch of stuff. First of all, where does 8 go, obviously? 8 goes for T. Can we agree? Okay. All right. Now, population doubles. Do you guys understand doubles? I'm just going to put a 2p for the y, and your p, we just keep it the same. Okay. Now, if you want, you can put p as 1 and this is 2. It doesn't matter because, well, let me just say this. Let's just keep it that. So p is p, and it doubles, so is 2p as your final population. We good? What happens to the p? They what? Cancel. Okay. And next we get this. 2 equals to e to the power of r times 8. We good? We want to isolate for r basically, so we log up both sides. I chose log with a base of e so that this can what? Cancel. That moves over and becomes a big R times 8. And I get that. Divide both sides by 8. And R equals to 0.125. Okay? All right. And so the value of K, which is the same as R, okay, is 0.125. That's your growth rate. Okay? In this case, it's a decay. Okay? All right. Give me 1 second. Okay. Now, boom, boom. I misspoke on it being a decay. Anyways, minor detail. Okay. Let's go to this. Let's look at this example if we even need it. This is the same thing, but instead of isolating for R, we're isolating for T, but it's exactly the same thing. You're going to use PERT, okay? And you just plug in everything, okay? It says half-life, so what you can do, okay, this says half-life, so what you can do is you can go P here, and then 0.5 P there, okay? And then you plug in, this is your rate, okay? They just disguised it there, and you just put it there, okay? That's your rate, all right? Because, what's a good way of explaining why that is rate, okay? Oh, that's your rate. That's literally what derivative means, rate of change. Okay? All right. Now, let's go to this example. Okay? Newton's law of cooling. Okay? Newton's law of cooling. This is just use this formula over here. Okay? I would just literally memorize this formula. Okay? This is basically just taking the PERT a little further. You can see it's built off of PERT. Okay, do you see the ERT in PERT as part of the equation? Okay, so it's already part of it, so it's just built off of it. Okay, now Newton's law of cooling, so watch this. T sub S is surrounding temperature, T sub 0 is initial temperature. Okay, regular T is final temperature. Maybe you can call this TF. Okay, let's see if we can get away with that and call it TF. I don't really see the TF in textbooks, but let's just see if we can get away with that. Okay, now check this out. Hard-boiled egg at 98 degrees initial temperature. Okay, all right. The surrounding temperature, the pan, which is what's in the pan, is 18. Are we good? Okay. All right. After 5 minutes, that's T, your egg's temperature, your final temperature after 5 minutes is 38. Are you guys with me? So watch how I plug in here. I mean, you can already see it. 38. Let's get some oranges. Boom, boom. Let's get gray. 5 and green. Are you guys with me? Now we're just going to isolate for R. Watch this. Okay. What's 38 minus 18, everyone? 20. What's 98 minus 18? 80. Okay. 80. And we get 5 times R. Okay. Now, isolate, we did it on this slide right here. Okay, whoops, on this slide over here. You basically log up both sides and then divide by 8 over here. So we're going to do the same thing. We're first going to divide both sides by 80 and get 0.25. Log up both sides and this moves over and divide it by 5. Does that make sense? Do you guys understand how I got to this R right here? We good? Now, we are 80 to 90% done with the problem. Now I'm going to plug the R back in. What's a color I have not used yet? Pink. I'm going to plug the R back into this general equation and plug everything the same, except instead of TF now, that you see, I'm going to, instead of TF being 38, I'm going to use 20 now. Okay, because it says how much longer will it take the egg to reach 20. So I just plug this in for TF and then solve backwards for T for the gray. So let me show you what I mean. Okay, let me show you what I mean. So you can see I have the general equation down here. Okay, orange gets reused. Orange gets reused. Same thing with 98 gets reused. Okay. And then the R right here. Boom. Okay, we now know the R. How much longer? We don't know the T now because the T was given before to get to 38. But we don't know the T to get to 20, so we leave T blank. Does that make sense? Okay. And TF, we're going to use this hot pink 20 because that's your new final temperature. Does that make sense? Okay. And then you just plug in and solve backwards for T. Okay, I'm going to recap on that concept. Give me 1 second. Boom. You can see how most of the numbers stay the same. This should be in parentheses, my bad. Okay. Most of these parentheses stay the same. Or highlights, sorry. Okay. Stay the same. Boom. And you solve backwards for T. So, look, most of the highlights stay the same. The only thing that's different, okay, the only thing that's different is that we plug in 20 in for this, and we don't use the 5 for the T, because the 5 applies to the 38 degrees, not the 20 degrees. Does that make sense? Okay, so we're almost done here, folks. Now, we just, okay, subtract these two. Again, I'm going to recap on what happened in a bit. Hang on. What's 20 minus 18? 2. 98 minus 18. 80. And then again, divide both sides by 80. You're going to get 2 over 80. Log up both sides, log base E. So it cancels here, this, and then divide by divide by this to get T. Okay? So maybe I should write that out. Okay? So you're going to get this. Here, let's move this up. Boom. Okay? Here, 2 over 80. Okay? Let me make that a, okay, log up both sides, log base E, boom, tilt that tilt it. This cancels. Okay, this moves over, and you end up getting this cancels, that moves over and becomes a not exponent, and ln. Okay, boom, 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 ln. Are you guys with me so far? Okay. And now you just divide, you hit this up in your calculator and divide it by this. Okay, divide it by that, and you get t. And t is going to be like 13.30, I believe. Yep. Okay. Now let's recap on what happened conceptually, because there were a lot of algebra details, but let's understand the concept. Okay. So we have this general concept over here. Okay. And we don't pay attention to this right now. Okay. We plug in for the initial temperature, orange 18, the final temperature in this with the 38, okay? This is your first final temperature that we're using. We're doing all that to solve for what, folks? We're doing all that to solve for what? R. Once you find R, okay, plug that into the general equation. But now your new final temperature, because the actual final temperature they're asking about is what? Not 38, but what? 20, and solve backwards for the T instead of the R that we solved for earlier. So we're recycling this equation again for this last part that I crossed off. Does that make sense? Okay, and we're solving backwards for T. Now it says how much longer, so it's not really 13.3 because that's total time to get from 98 to 20, okay? But to get from 38 to 20, if 5 minutes pass by, what do we have to do with 13.3 and 5? Subtract the 5 and you get 8.3. So it took an additional 8.3 minutes to get from 38 to 20, which is what it's asking for. Okay? All right, you guys get started on classwork. Let me explain this proof right here. Okay? Now, so again, I want to quickly explain this proof, how to get from this yellow to that yellow right there, okay? This is the derivative, and the antiderivative is going to be this. So we're going to antiderivative, okay? Let me hear. We're going to antiderivative both sides here, okay? This, and this becomes ln of y. And when you antiderivative that, you are going to get k times t, okay, plus the c, okay? Now what we're going to do is put an e, okay? We're going to put an e on both sides. Fellas over there. Fellas, okay? Now, okay? So we're going to put an e to both sides, and we end up getting this right here. Remember, ln is the same as log base e, okay? And this cancels, and this becomes a non-exponent, becomes a big, okay? A big number, okay? A base, basically, okay? So this becomes a y, and anywhere you see plus with an exponent, you can rewrite it with the same base of e and do times, okay? And now this is basically a big constant, which becomes that. Okay, so I'm just showing you the proof of how to get from here to here. Again, anytime you see this, it's implied it's this, which is essentially the same as PERT. Okay, and that's all, folks. Let me see if I need to clear anything up over here. Nope. I am good. Thank you for tuning in, folks.